Okay, here is our 10.3 continued. This is going to be a lot more of you doing some of it and then watching me go over it. So our first one here, this bar graph shows the results for rolling a number cube 300 times. First, for part A, I want you to find the experimental probability of rolling an odd number. So this is very similar to what we did in our last lesson video for the first example. So go ahead, take a second, pause the video, do this problem, and then come back when you are done, and we'll go over it. So let's go over this. Rolling an odd number, let's look at all of our odds, 1, 3, and 5. You have to figure out how many times did we roll a 1, 3, and a 5, which it has it here for you nicely. Then what you needed to do was add those together. When you add those together, you should have gotten 147. For a probability, we're going to put it over the total number of trials, which they told us was 300. So our probability was 147 out of 300, or you actually can simplify this to 49 out of 100, which would be 49% if you wrote it as a percent. Again, you can keep it as a fraction. Doesn't matter how you write it. All right, part B now. How does the experimental probability compare with the theoretical probability of rolling an odd number? So guys, this is our experimental probability, what we just found, okay? Theoretically, if you have a number cube, how many numbers are odd? Well, we have 1, 3, and 5, so it would be 3 out of how many total sides are there? 6. So your theoretical probability would be 1/2, or 50%, right? So keep your percent sign. We're comparing 49% to 50%. Aren't they pretty close, the theoretical to the experimental? So I'd say they were very close. 49% is just a little less than 50%. They're only a percent off or a little bit off. But it should be your experimental. The more trials you do, the closer you should be getting to the theoretical. They should be close. All right, now it is your turn. I'm going to have you pause and practice some if you want to do some on your own. Pause and do this first problem modeling, parts A and B, and then press play when you're ready to go over them. All right, let's go over these. Part A, what is the theoretical probability that a randomly chosen student is female? So if there's 16 females to 20 males in the class, the probability of choosing a female should be 16. So there's 16 females out of, now be careful, how many total students are there? Add these together, it would be 36. Or we can simplify that to 4/9. 1 week later, there are 45 students in the class. The theoretical probability that a randomly chosen student is a female is the same as last week, so it's still 4/9. How many males joined the class? So now we have to be careful. We could figure out if there was 4 out of every 9 are females. If there's now 45 students, how many of them are females? We could figure that out first. So I know that 9 times 5 is 45. So 4 times 5 is 20. That means there are 20 females, but they want to know how many males joined the class. So if there's 20 females, that leaves 25 males. If we had 20 males last week, how many males joined the class then? 5 males joined the class. So our answer is 5 males. All right, we have another problem here, this game show problem. Go ahead and pause and try this on your own. Press play when you're ready to go over it. All right, let's go over this. On a game show, a contestant randomly chooses a chip from a bag that contains numbers and strikes. The theoretical probability of choosing a strike is 3 out of 10. If the bag contains 9 strikes, how many chips are in the bag? So let's take a look. We have 3 out of 10 that's our probability of choosing a strike. I want to know if there's 9 strikes in the bag, how many chips in total are in the bag? So So now we're just solving this. I know 3 times 3 is 9, so what's 10 times 3? Our answer should be 30. All right, our last example here, we have a number sense. If you want to pause and try it on your own, go for it, and then press play when you're ready and we'll go over it. All right, let's take a look at this problem. The table to the right shows the results of flipping 2 coins 12 times each. These are our results. So when we flip the 2 coins, they got heads and heads, both landed on heads twice. We got a heads then a tails, that happened 6 times. We got a tails then a heads, that happened 3 times. And they flipped 2 tails, that happened 1 time. Part A, what is the experimental probability of flipping 2 tails? So this was our experiment. Look at the 2 tails. How many times did that happen? It's out of 12 trials. So that happened 1 out of 12 times. Now, the second part says, using this probability, how many times can you expect to flip 2 tails in 600 trials? So what you'd have to do is you'd have to set this up as a proportion with 600 as your total trials. I want to know, what would you expect? Well, I know 12 times 50, because 12 times 5 is 60, so 12 times 50 is 600. So 1 times 50 is, I would expect it to happen 50 times. Let's do part B. The table to the left shows the results of flipping the same 2 coins. Now they flipped them 100 times. So out of 100 times, they got 2 heads 23 times, and so on. You can read that table like we did before. What is the experimental probability of flipping 2 tails? So we're looking at the 2 tails. That happened 22 out of 100 times, or we could simplify that to 11 out of 50. Now I want to know, if we use this, if we expect 600 trials, how many times would you expect it to happen? So I think 100 is easier to get to 600 because we times 6. So now we're solving this. What's 22 times 6? You should have gotten 132 times you would expect it. Last one, why is it important to use a large number of trials when using experimental probability to predict results? So I'm going to explain that to you. The larger your number of trials are, the closer you get to the theoretical probability. So you want to do, the more trials you have, the better results you'll have. So larger number of trials gives better results. It'll give us better results and they'll be closer to our theoretical. Okay, so you always want more trials. All right, guys, that is it for lesson 3.